So in the last class, I told you about the state function and non-state function. So what I told you is, suppose you have a gas here. Suppose you have a gas here, and you just heat it from, let's say, 25 degrees centigrade to 30 degrees centigrade here, 30 degrees centigrade here. So you heat anyway, you heat slowly, you heat fast, you do one way or the other way. So the temperature change is always same. 30 minus 25 is 5 degree, right? All right. So can anyone hear him? I think you should be able to hear me. Yes. Okay. Good. So. Or if you are measuring the pressure, let's say the pressure here was 2 atmosphere, and by somehow you change the pressure to let's say 1 atmosphere, so the pressure changes no matter how you do it. That pressure change is always 2 minus 1 is 1 atmosphere, right? So that kind of thing is called the state function. Temperature change, pressure change. Actually, I was just repeating the last class lecture. So I posted yesterday a file, so I will talk about that. So this is just the revision of the last class, last slide. So all right. So temperature change, pressure change, volume change, they are state function. No matter what you do, the change is the same. Yeah. But if you are calculating the work, so let's say I'm calculating the work. So I expand this gas from, let's say, 2 liter to 5 liter here, 5 liter here. Now I want to, my job is to calculate the work. So work is calculated here. W is equals to P dV. So P is a pressure. How much pressure it is pushing it down from outside, and dV is the 5 liter minus 2 liter is a 3 liter, right? So 3 liter. So if you do very slowly, this P value will be big, and then the work value comes big. But if you do very fast expansion, this P value will be small and work will be small. Make sense? So if you do, expand the gas very slowly, you get a lot of work due to this large P value. But if you are doing this expansion very fast, this P value will be small and the work value will be, you don't understand in this class this concept. If you take the thermodynamics in future, you will understand. Yeah. So don't worry too much about it. So if you do expansion one way from 2 liter to 5 liter, you get one value of the work. If you do expansion another way from 2 liter to 5 liter, you get another value of the work. So the value of the work is different the way we expand the gas. Make sense? So it's a path. It's the different way. So in thermodynamics they call path, but basically it's the way how you expand the gas gives the different value of work. If you expand the gas very slowly, you get a large amount of the work. If you expand the gas very fast, quickly in 1 second, you will get the less value of the work. There is a reason why, and there is a lot of explanation in other books. So in this class, we don't discuss that. So just know that work is non-state function, and then temperature change, volume change, pressure change, these are state function. Yeah. So there are homework problems. Is a volume is a state function or not? Temperature is a state function or not? Work is a state function or not? So those kind of things. So good. Now we start the new slides that I posted yesterday evening. So I plan to finish it first today, or if not, maybe in a little bit in next class. So there are two kind of equation you see in first law of thermodynamics. Somebody write like this. In some book, if you look this one, dq is equals to du plus dw, like this. Okay. If you look in the same book, another book, in another page, they may write like this. So here is a du is equals to dq plus dw. So somewhere you may see something like this, somewhere you may see something like this. This is not a, if you look at the math book, if you write the equation like this, that's not true, right? So dq is always equals to du plus dw. That's That's the equation. But some book write du is equals to dq plus dw. How is it possible gq is equals to du plus dw and du is equals to gq plus dw, right? That's not possible, right? So the difference is that, let's say you supply the 100, this is a gas here, you supply 100 joule of heat energy here. You supply the 100 joule of heat energy here, 100 joule. So you put 100 here, 100 here, right? 100 joule of heat energy. Now, some of the heat, you supplied heat is absorbed to do the work. Maybe this piston moves a little bit up, and then to expand this gas, maybe 20 joule heat energy is absorbed to expand this gas, right? To do the work. So that is the dW, that's 20 joule. So how much heat is used to increase the temperature then? So this is 100 joule, this is 20 joule. There must be 80 joule here, so that 80 plus 20 equals to 100, right? So this is the first law of thermodynamics. So this is most state way of doing things, right? Make sense? So this is the law of conservation of energy. So you supply 100 joule of heat energy here, 20 joule is used to push this piston up, and 80 joule is used to increase the temperature of this gas, right? But in another place, they may write this equation. So how do we do that? So we can do like this. So dq is a heat absorbed here. So we write the plus 100 here. dq is a, so we do the sign convention here. You see, so in this one, I was just doing that directly how we do the money thing or the everyday life thing here. But in thermodynamics, sometimes they do like this. So dq, why plus? Because heat is absorbed. So when heat is absorbed, they write the plus 100 here. Now dW, what is dW? So we are expanding the gas. The gas expanded, so the piston is moved up. So they give that to the minus sign. So they write here minus 20 joule, like this. Make sense? Because I'm just doing the expansion here. Heat is absorbed, so we give plus sign. Gas is expanded, so we give minus sign there. Make sense? So I write the minus 20 joule. Now my job is to calculate du here. So du would be equals to 100 minus 20 would be 80 joule, plus 80 joule. Same thing, see, 80 joule here, 20 joule here. So it just, in this one, I didn't do any sign convention. I just put the number and I just use my mind. Okay, I give the 100 joule here. So if 20 joule is used to push the piston up, 80 joule must be the here to balance that, right? It's very simple way. So another way, you can do like this also. So ultimately, the heat absorbed dq must be equal to the sum of those two numbers, dw plus du. Yeah? Make sense? So I wrote that in the first slide, so you can read yourself. Yeah? I posted this in yesterday evening, so just read those, and I wrote those concepts here. Yeah? Good. So ultimately, no matter what you do, 100 is equals to 80 plus 20, right? Or 70 plus 30, or 50 plus 50. So you are just dividing that big chunk of it into two parts. One to expand the gas or the move of the piston, another is just to another part is just to change the temperature of the gas, right? So don't get confused there in the sign convention. Now I'm going to do in the second slide. Now I'm in the second slide on enthalpy. So this is termed, there is a term called enthalpy. What is enthalpy? So anything we do in our laboratory here and we measure the heat, that is called enthalpy. So if the pressure, if you are doing the reaction in open vessel, so this is open vessel, right? Open vessel, VESSEL, open vessel. Is it closed? No, is it open? So I didn't, so you may put a cap here, but cap still has a small hole here. So if there is a something, if you are doing the reaction in open vessel, or if you are working in thermodynamics in open vessel condition, any heat change you find there is called the enthalpy. Make sense? But if you are pushing with something, so you close this cap here, now you put a big weight here, and you are pushing it. Somehow you are pushing it. That's not enthalpy. That's why we need to treat that different way. Make sense? So if the vessel is open, so you have a cup here. This cup is open. Is here some water, and now you are doing some reaction, and you measure some heat here. So that heat is called the enthalpy. Make sense? Open vessel in atmospheric pressure. So here is a definition. So let's say you do some reaction, and the heat is observed as dq. So here, if you are heating this one, or heat is producing here, that is dq. And let's say there is a some, so du plus dw. So this is our first law of thermodynamics, right? Now, what I told you, if you are doing this reaction in open vessel, dq is called dh. So it's the same thing. So don't use this one. So just use this one. dq is dh. At what condition? The condition is you are doing the reaction at 1 atmospheric pressure, meaning that you go to the laboratory, take an open vessel, do reaction, measure the heat. The heat you measure there, what happened there is called the enthalpy. Make sense? But if you are pushing this gas with a great force down here, and then you are measuring the heat, that heat is not the enthalpy. All right. So any heat change in the system, when we are doing the reaction at 1 atmosphere pressure, 1 atm pressure, meaning that 1 atm pressure means this vessel is open. So there is an atmosphere outside. That atmosphere is working there. Yeah. Good. So there is a difference, a little bit difference between the enthalpy and the heat. So heat is a measured thing. So enthalpy is when we do the reaction in open vessel and we measure the heat, and that heat is called enthalpy change. All right. So good. So this is enthalpy. So that dh is called enthalpy change. So we'll do the enthalpy example here. So I'm in the slide number 3, and there is an equation. It says H2O plus S2O is broken to give half O2, and delta H is equals to plus 241.8 kilojoule per mole. So this is called enthalpy. So dH is called enthalpy. So meaning that you have a water here, 1 mole water. So you have 1 mole water. 1 mole meaning that 18 gram water. You have 18 gram water here, 18 gram water here, and go to the laboratory and break this 18 gram water into hydrogen and oxygen like this. And to break that, you need to give 241.8 kilojoule heat energy there in open vessel. I don't know at what, if you put the pressure here, a lot of pressure, maybe this number is larger, maybe 500, 600, 800. If you put some weight here and do this reaction, maybe this number is very big. But if you are just doing this reaction in open vessel, there's just 1 atmospheric pressure. So to break 18 gram of water, that is 1 mole of water, you need to supply 241.8 kilojoule of heat here, and then that will break. Make sense? So this is a plus sign. We are supplying the heat into the system to break this one. So let's do the other way. So let's do this way. H2 plus half O2. Half O2 gives H2O. So like this. So you can do it another way like this, right? So here we are breaking the water into hydrogen and oxygen. Here we are combining hydrogen with the oxygen, right? Make sense? And then the how much heat we need here? So the delta H heat we need is minus 241.8 kilojoule. So what we are doing here is we are mixing hydrogen and oxygen. Hydrogen and oxygen here, and we are producing 18 gram of water, 1 mole water. 18 gram water. 1 mole means 18 gram, right? So here in the cup, we are mixing hydrogen and oxygen to produce 1 mole of water. So what we are doing here? So the hydrogen and oxygen are burning together, meaning that you just light this mixer, and this gives out 241.8 kilojoule of heat energy out. Make sense? And we are doing this, burning this in open vessel. Open vessel. We are not closing this and we are not tightening this. There must be some opening. Make sense? So this is a endothermic reaction, because to break this one, into hydrogen and oxygen, you must supply energy from outside. So that's endothermic. You give the energy to happen this thing. But in this one, they are just doing the burning like the fuel. So just you light it and they burn it and they get a lot of energy out. So this vessel becomes hot. So this is exothermic. So minus means exothermic, plus means endothermic. So this means if you do something here with the water, that system is going to be cooled. If you do something like this, you burn it, and then the system is the reaction vessel is going to be hot. Make sense? So if you see the minus there, that's exothermic, meaning it's giving out the just fuel burning. So if you burn the fuel in your car, the car engine becomes very hot, right? So that's exothermic reaction. Make sense? Good. So this is enthalpy. Why we call enthalpy? Because we are doing this reaction at open vessel, that is in 1 atmosphere pressure. We are not pushing the mixture by putting weight there. Did I make it clear? All right, so let's go to, so there are some questions here. So they're pretty easy questions. So let's look one question in exam, slide number 4. So the question is like this. So CS3H8 is a propane gas. So if you go to the quick trip or somewhere and you buy a cylinder, and that cylinder has this gas, propane gas, yeah? Propane gas, and they are burning it in oxygen. So this is a balanced reaction. So like this. So it is saying the standard molar enthalpy, meaning that you have a 1 mole of propane. Molar means 1 mole. You are burning the 1 mole of enthalpy. Sorry, 1 mole of this gas. Standard molar means you are burning 1 mole of this guy, 1 mole of this guy, and if you burn that 1 mole, how much heat energy it gives out? Minus 244. What this minus means? If you burn it, if the heat is coming out, it's warming us, right? When we burn the fuel, it warms us, right? It gives the heat. So that means that this much heat is coming out. When you burn 1 mole of this gas, this much heat comes out. Now the question is, what is the standard enthalpy change for combustion of 3 mole of propane? Now 1 mole gives this much, 3 mole gives how much? Maybe I write here. 3 mole gives how much? 3 mole gives how much? Just write X. Make sense? So it's a math trick, so you can do any way you like. So the question is, if I burn this 1 mole of thing, I get this much heat. How much heat I would get if I burn 3 mole, X joule of heat. So you can just mentally calculate, just multiply, right? 1 mole gives, let's say, 1 pen costs $5, 3 pen costs how many? $15, right? Yeah, it's simple, right? If 1 pen costs $5, 3 pen costs how many? 5 multiplied by 3, right? It's simple, just like that. So you can do the direct multiply, or you can just take the ratio. X by minus 2044 is equals to 3 by 1, like this. So you can take this value this way here. So X is equals to 3 multiplied by minus 2044 by 1, meaning that's the same thing. So that many joule. Easy? But you don't have to do how I am doing here. If you know this kind of thing from your high school, you can do your way. Yeah. So it's basically saying just like this. If 1 pen, if I have to buy 1 pen, I need $2,000, $2,044. If I want to buy 3 pen, how many dollar I need? Right? Just multiply by 3. Make sense? You don't think complicated way. Good. So another one in slide number 5 is exactly the same. I already converted to mole to gram and gram to mole. So you can just practice yourself in question number 5. Slide number 5. Now let's talk about the slide number 6. So somewhere you might see mole to mole, and somewhere they might say, oh, it's changed to gram. So you can just convert that to the mole to the gram and calculate in terms of the kilojoule per gram or something like that. Yeah. So this is already there, so you can read yourself. Let's see. This is important. So this is very simple, but this is really important slide number 6. Very, very important, yeah. So all the thermodynamics in the world is done like slide number 6. But this is really simple. So you do this experiment, you may need $10. But if you go to the big laboratory, the same instrument they design maybe multi-million-dollar. So it is a very simple equation, simple thing, and all thermodynamics is based on this experiment. Yeah. So how we measure the heat change in laboratories like this? So take a 2 coffee cup. So you know coffee cup, right? You go to the Dunkin' Donut and bring the 2 coffee cup, right? So they are made of styrofoam. So take this one. So this is 1 coffee cup, and take another coffee cup. Put another coffee cup inside like this. So I have 2 coffee cups put together, right? So coffee cup. So this is the most simplest, very effective vessel to do the thermodynamics work in laboratory. So this is the coffee cup. So how many coffee cup I have? I have 1 coffee cup outside. I have another coffee cup inside. So so I just put like this. So 2 coffee cups. Now, so this is called the calorimeter. Now coffee cup we are calling it as the calorimeter. Now what you do is put some water. Put some water here. Put some water or whatever you want to study. Put that water here. So let's measure the mass of this water. So the mass of this water is, let's say, I'm just assuming one number here. Mass is 10 gram. 10 gram. The mass of water is 10 grams. So I put 2 coffee cup here, and I put 10 gram water in the coffee cup inside, right? Make sense? Now what I do is I put the coffee. I put a thermometer here. I put a thermometer here like this. So I just put water and I put the thermometer and measure the temperature. So T1 is equals to, let's say I measure the temperature, and that was 25 degrees centigrade. Very simple. You can go to the laboratory. You can go do this in your home yourself. Yeah, it's very simple. And then 25 degrees centigrade. So it's showing 25 degrees centigrade. 25 degrees centigrade. Now, what you do is, whatever reaction you want to do, put that thing inside. So let's say I want to put sodium hydroxide here. So I'm going to put some sodium hydroxide here, NaOH, sodium hydroxide. So let's say I put 2 grams of sodium hydroxide here, right? So I'm going to put sodium mass of sodium hydroxide 2 grams. So I just put this 2 grams sodium hydroxide here, right? Now immediately after putting that, I'm going to cover this coffee cup with the cap like this. Make sense? Did I make it clear? Very simple experiment, yeah? So first of all, I take 2 coffee cups from Dunkin' Donuts, and then I put one after another. So this is outside coffee cup, this is inside coffee cup. In that inside coffee cup, I put 10 gram water. You can put 5 gram, 10 gram, 15 gram, doesn't matter. 10 gram water, and then I put the thermometer and measure the temperature. After measuring the temperature, I put 2 gram of the sodium hydroxide here. You can put 3 gram, 5 gram, 7 gram, it doesn't matter. Yeah. So you can put whatever you like. And then I immediately after that, I put this cap here. Why do I put this cap there? So that the heat doesn't go lost to the environment, right? If I don't put the cap there, the heat is going to go out in the air, right? So I just wanted to prevent that heat. So I put it here. Now record the temperature. So after that, after putting and stirring this, stir a little bit with this thing, so that all sodium hydroxide dissolve, and record the temperature. So record the temperature. So maybe the temperature is to 40 degrees centigrade here. Easy? Anybody can do this experiment, right? How simple it is. And this is the so expensive thing to do these days in big laboratories. So you are determining the calorific value of food. They are doing different kind of the battery work with different kind of things, medicines, and they make a very, very expensive instrument based on this one, maybe multi-million-dollar one instrument. See how simple it is, right? So now how much heat is produced here? I just want to measure that one. Now what is our equation? Q is equals to MC T2 minus the T1. That's our equation, right? Always the fundamental equation for thermodynamics, always this one, Q equals to mc T2 minus T1, right? Now, how much mass I have in total? So take this m as a total. So here is a 2 gram, here is a 10 gram. So total mass inside here is 12 gram. So I put that 12 there. Make sense? 12 gram. Now, what is the, I don't have the specific heat capacity value of LOS, so we just use the specific capacity value of water. So that is 4.18. So we have been using the same value from long time. The specific capacity of water is 4.18. And what is the temperature difference? 40 minus 10, 25. 40 minus 25. So calculate this number and you will get 752.4 joule. How simple it is, right? Did you do it in lab? Very simple, but very effective. You will do this experiment in, I think, 11th, maybe in our Chem 0116, Chem 106, I think it's the 8th laboratory, so you will do this, yeah? So like this. So you see how simply we could find the value of heat. How much heat is produced here? That much heat is produced here. So I was mixing 10 gram water and 2 gram sodium hydroxide together there, and then this cup becomes very hot. And when I touch it, it becomes very hot. So how much heat it produced? So I did a calculation and it produced 750. So I like this experiment a lot actually. This is most simple, very effective, very easy to understand, and all the dynamics is based on this principle. Listen? Very good. So I put one homework problem from here, you will see. So just you are just using the C value of water, 4.18, the mass, you are summing these two together, and this is the temperature difference at the beginning. And yeah, so I think I teach it really good, this one. So I hope you understood it. So, so there is a problem in the coffee cup calorimeter in this slide number 7. So probably you can do yourself this one, yeah? So try yourself and how you feel. Kilojoule, is this in mole or? Yeah, just read it, and if there is a mole, convert to the gram, and then you try to do that. So it really is, yeah, all those problems are like that. So read this coffee cup calorimeter very well. So I'm going to put that in exam too, yeah? So you did a lot of thermodynamics and you did not understand this and you don't know how to use this equation, that's bad, yeah? So just read that a couple of times. And so there are a lot of problems like this. I think you just do a little bit math, and maybe I just do because I have some time here. So let's do this coffee cup calorimeter, slide number 7 problem. So slide number 7. So in slide number 7, when 6.50 gram sample of solid sodium hydroxide dissolved in 100 gram of water in coffee cup calorimeter, the temperature rises from 20.6 to 37.8. Calculate the delta S for the solution process. So it's pretty simple. So it is in terms of gram or in terms of mole. Just we need to do that one, right? So let's do. You have a coffee cup calorimeter here. So 2 coffee cups here. So he put 6.50 gram water. 6.50 gram water, and then how much sodium hydroxide? No, 6.50 gram sodium hydroxide here, and then 100 gram of water together in that coffee cup calorimeter. And he was covering this one and doing the reaction. And at the beginning, the temperature was at the beginning, before mixing, it was 21.6 degrees centigrade. After mixing and stirring, T2 become 37.8 degrees centigrade. So what is the heat produced there, right? Make sense? So he put the 100 gram of water here, and then measure the temperature 21.6, and then he added 6.50 gram of NaOH and power the tap, and then stir up for a while and measure the temperature, and he got the final temperature, this one. So how much heat is produced by mixing these two things is like this. Q is equals to mc T2 minus T1. So m is the sum of this one and this one, that is 106.50. 106.50, and the C we always take for the water, because the water we know very well, 4.18, and then T2 minus T1 is 37.8 minus the 21.6. So how much we got here? That gives you 7212 joules. So that many joule of heat energy is produced, right? Exactly same thing that I did previously. Now you can convert this into kilojoule if you want by dividing by 1000. So that gives you 7.212 kilojoule. So 7,214 joule is 7.2 kilojoule, right? We have to divide by the 1000 to convert to kilojoule. So the question was, calculate delta H in kilojoule per mole. So that's the question here. So if the question was how much heat is produced, I would just stop here and I'm done, right? But the question was, okay, convert that into kilojoule per mole term. So this is the total heat, kilojoule. So I measured the heat and how much heat I produce, kilojoule, right? But this is asking, convert this into kilojoule per mole of sodium hydroxide. So just put it like this. So 7.212 kilojoule is produced from how many? So that 6.50 is 0.1625 moles. So this heat is produced from 0.1625 moles. So the 6.50 gram is that many moles. So I was putting NaOH 6.50 grams. So I converted this gram to moles, right? By dividing with 40, and so that is that many mole. So when I put this many mole, I got this much heat, right? But the question is, calculate the heat if you take 1 mole of sodium hydroxide, right? So how much would you put produce the heat? So I put the 1 mole here, and I don't know what is the value of X. So for this many mole, I got that much value of heat. For 1 mole, how much heat I would produce, I don't know, right? So I need to calculate that, right? So what I do is, I just take the ratio equal here. I just calculate the value of X there, multiply it, and you can easily calculate. Make sense? So if in exam I say, oh, calculate the total amount of the heat from that 6.50, you would stop here. If I ask you in terms of 1 kilojoule per mole, so 0.1625 was a 6.50 grams, so I converted to mole. So burning this many mole, I would give, putting this many mole of sodium hydroxide in that 100 gram water, I would get this much heat there. If I had put 1 mole, that is 40 gram of sodium. If I have added 40 gram of sodium hydroxide, how much heat I would get, right? It's just like, why, if I get a 0.1 gram of something, I would pay $7.2. So if I buy 1, how much I would pay, right? It's a simple calculation. Make sense? So maybe you are just thinking too much. It's just simple when you go to the store and how much how much money I have? Okay, I want to buy 1 pen. I need $5, right? So if I want to buy 10 pens, how much money I will spend? Just like that, right? So good. So you do that, and same thing here. If you see the molar enthalpy, molar means 1 mole. If you are putting 1 mole, so let's say I just give one idea. What is the difference between total enthalpy and the molar enthalpy? So let's say I put This is a coffee cup here. So let's say I put a 200 gram of water here, 200 gram of water here, and let's say 80 gram of NaOH, 80 gram of NaOH, 80 gram of NaOH. So at the beginning, so I put 200 gram here, so put the thermometer, measure the temperature, T1 was 25, put the 80 gram here, and the stir it, cover it, and then measure the temperature, T2 was, let's say, 75 degrees centigrade. So one thing is how much heat energy would produce. You just use the equation Q is equals to mc T2 minus T1. So you have the M is 200 plus 80. 280, C is 4.18, T2 is 75, T1 is that one. That many joule of heat energy would produce, right? And that increase the temperature. Simple. Now the question would ask you how many mole, what is the energy per mole of the mixture? When you mix, what is the heat energy per mole? So this one, 80 gram, you need to convert that into moles first. So 80 gram would be, so if you are working with NaOH, so the molar, look the periodic table and find the mass. So 1 mole is equals to 40 gram. So 1 mole is 40 gram, 80 gram would be 2 mole, right? Make sense? So 1 mole is 40 grams. So this comes from the periodic table. Now 80 grams. So you put 80 gram here. So how many mole is that? 1 by gram, 40 gram here, and then 1 mole here. Gram cancel. So 80 by 40 would be 2 moles. 2 moles. So that is 2 moles of sodium hydroxide, right? Now whatever the heat you get from here. So what you do is you just put that number here. So maybe. So the 2 moles, so the 80 gram is 2 mole, so 2 mole from here you might got, I don't know how much, so 50, maybe 10,000, maybe you got around 10,000 here, 10,000 here, so for 2 mole, you get, from this equation, maybe you got 10,000 joule. Now, your job is to calculate the energy per in 1 mole, so you would put 1 mole, and then you put X here. So if 2 mole need 10,000 joule, 1 mole need how much? 5,000, right? Simple. So you just do like this, take the ratio, and you calculate the value of X. Make sense? Easy. So it's one step further. Now, yeah, just try this problem yourself and see. Now we have only one concept left in this one, that is called Hess law. Yeah. So the Hess law, they call the Hess law. Sure, I want to put this question in exam as well as in homework, the coffee cup calorimeter. So now, so the math is too much in our class actually. So the book does not have put this much math here. So I like to teach concept rather than math. So Hess law. So this is a Hess, Hess. The guy's name, maybe surname is Hess. So he gave a law. That name is Hess law. Hess's law. So what is Hess's law? It's a very simple concept actually. So let's say you have a chemical A, and you can directly convert A to C and measure the heat. How we put it in that coffee cup calorimeter and mix NaOH and water, and then whatever that produce. So directly you did that, right? So this is one way. So how much heat you produce here? So that is called, let's say Q1. Q1, or let's say H1. Rather than Q1, let's say H1. Why I write H1? Because it's the enthalpy. We are doing this reaction in open vessel. I could write the Q1 too. It's the same thing, but H is more relevant because we are doing the reaction in open vessel, right? At 1 atmospheric pressure. So like this. So let's say you have a coffee cup calorimeter here, and then you put water and NaOH, and then you measure how much heat is produced here, and that is H1. Make sense? We already know how to calculate that H1 value, right? So that's Q is equal to mCT2 minus T1. So now you can do this way, or This is one way. This is one way of doing things. Or you could do something like this. You take A. This is one way, yeah? One way, one part, one way, one way. You do another way. First, take A and break to B. Change to B. So maybe you change NaOS to first of all Na, O, and A. I don't know how many we can do. So don't directly change A to C. Change only A to B first, yeah? And then measure the heat. So maybe you got H2 amount. Maybe you got 10 joule here. Maybe let's say H1 was, you measure the heat and you got a 500 joule here. H2, A to B, so you might got 200 joule here. Converting A to B. Just exactly how we do in coffee cup calorimeter, right? And then take the B and convert to C. And maybe you got H3 here. The value comes to be 300 joule. Make sense? What I did here, I directly converted A to C. Yeah? And I measured the heat and that was 500. But here, I first take A and convert to B. And I got measured the heat 200. And I convert that B to C. I reach there and I got 300. Now you see here, so direct 500 is equals to 200 plus 300. So both way is the same thing. Make sense? So no matter how many steps you do the reaction, and if you sum the heat, the sum is always the same, right? So it's like I can go my office this way, or I can go to my office this way, or I can just go from here and there, sit for a while, and then stand up, and then go to another place, and I sit there, and then I walk to my office. And so no matter what I do, I did the same job. I go from here to my office, right? The same amount of work I do. Make sense? So it doesn't matter how many ways you do, but if you are starting from one place and reach to the same place, either directly, maybe by helicopter, right? So you take the helicopter from go to A to C, and you measure the change in energy was 500 joule. But here you walk, and you walk from A to point B, and walk from point B to C, and measure the heat change. They become the sum becomes the same. Make sense? So this is called the Hess's law. Easy? Good? Alright, so here is alright, so we're almost there. If we cannot finish, I will toss this in next class, and then we'll start another chapter. So here is a diagram in slide number 11. So he's writing like this. Okay, so I have a chemical and I'm measuring the heat when I change from A to E, right? So I have a chemical, I heat it, or I did some reaction, and it converts from A to E, and I measure how much heat I produce there, delta H. So that's the heat, like H1, H2, you can write anything. So this is the amount of heat, how many kilojoules, I don't know. Now you can convert A to B. You can go convert A to B and measure the heat. How much heat change you did? Delta H1. And then convert B to C. How much heat change from B to C? Delta H2. And then convert from C to D. How much heat change from C to D? Delta H3. Now convert D to E. How much heat change? Delta H is equal to delta H4. Now this is a direct path. You go from A to E directly, like you take a helicopter and go to home, right? Directly. And this one is, you just take one step there, you walk from A to B, and then you walk from B to C, and you walk from C to D, and then you are measuring the heat. So the total heat, direct path, delta S, and then many steps is delta H1 plus delta H2 plus delta H3 plus delta H4. Same thing. Make sense? So in one way, I'm just converting A to E directly in one step, and I measure the heat, and maybe I got 1,000 joule. Going from here to here, maybe I got 1,000 joule here. And then I go from A to B, maybe that heat was just 100 joule. And I go from B to C, and maybe the heat change was 500 joule. And then I go from C to D, maybe that was 200. Now, how much should be the delta H for? Then this 500, 200, 700, 800, I need 1000. So I need 200 here. So then that should be like this. Make sense? So 1000. So this is also 1000 joule. And then when I sum all these other way, they are also give the 1000. Make sense? Simple. Now, read the slide number 12. You can read the slide number 12 yourself. What I showed here is exactly the same. Yeah. So read the slide number 12 yourself. Now, I show you one concept here, so that you will use in the lab 6, I think lab 11. So let's see if I can do in 5-minute time. If not, I will do in the last class, next class. So now here is so we are doing the arithmetic. It's a very simple mathematics we are doing here, and he is giving here CS2 plus 3O2. So I'm in the slide number 13. So I have CO2 here plus 2SO2. So this is balanced like this. So I need to find what is the delta H value here. If I do this reaction, if I react carbon disulfide with oxygen, I take the coffee cup calorimeter and I mix some amount of carbon disulfide and I put some oxygen and I burn it or do something. And how much? And I measure what is the heat amount. That delta H is basically Q is equals to MC T2 minus T1 when we do this reaction in open vessel like coffee cup. Yeah, makes sense? Coffee cup is an open vessel because there is always some opening in that coffee cup. Yeah. So delta H and Q is same here because we are doing this reaction in open vessel. How much time I have? All right. So I need to find this one. How much is here? So how much heat energy I would get there? And the given here is C plus O2. So if I do this one, that it gives CO2. And the heat would be H1 would be minus 393 kilojoule per mole. And I have here S O2 SO2, and then that would give me minus S2 would be minus 296.8 kilojoule. Then I have here C plus O2 gives CO2. What is that? I did some mistake. C plus O2, C plus 2S. So C plus 2S. So 2S gives me CS2. And S3 would be 87.9. This is plus. 87. It said 87.9. This is also minus. It's a plus CS2. Oh, it's a plus here. It's a plus here. So maybe I can do this in next class. So I need to find this value here from this reaction. C plus O2 gives this much heat. So if I burn carbon with oxygen, I get heat out. So that's a negative sign there. And if I burn sulfur with oxygen, I get heat out. But if I want to do reactions carbon plus 2 sulfur combined to C, I need to give a lot of energy here. I need to put energy in this system. Make sense? So this is exothermic. So it's like the carbon and sulfur here are working as a fuel. But here to combine this one and this one, it's not working as a fuel. I need to put a lot of, I need to burn something outside and I need to put that heat there, and only I can do this reaction. Make sense? So this one is working as fuel because its heat is giving out. I burn the carbon and it's giving out this heat. And this is also, sulfur is working as a fuel. It's giving heat out. And CN2S, this is not working as a fuel. I need to, like if I need to boil water, I need to provide the heat from outside, right? So I need to provide a lot of heat here. So how much heat? 87.9 kilojoule heat to happen this reaction. So this is endothermic, and I need to supply heat. These are exothermic, because once I burn them, they are giving me a lot of heat, right? Make sense? So I need to use these 3 equations to get this equation, and I'm done. Yeah. So how much time I have here? So maybe I teach this concept in next class and then we finish this. Yeah. Good. So you can read yourself how much you can understand that slide number 14, 13 and 14. Yeah. But I will teach in next class. Have a good weekend, Katie. Thank you very much. All right.